we've been talking a little bit around this, and it's now deep enough in the quarter, and we've seen enough examples of differential equations, like physically motivated differential equations, that we can now go through this really important idea in detail with examples. So this is Sturm-Liouville's theorem, and it looks like a mouthful, and there's some fine print that, I'll just tell you right now, everything you're going to see satisfies the boundary conditions, so you don't have to worry too much about that. But this is what it says, and we're just going to rewrite this, give an example of what it means, and map it onto the things that we've been doing for the past month. So I have a differential equation, so this is a differential operator. It could have some, like x squareds plus beta, and then some derivatives in it. And we're used to seeing things where differential operator acts on thing, and I get 0. And we care about it on some domain. So this could be the entire real line, I'll just say that. And it's got some boundary conditions. Just squint for a second and realize that this is very, very reasonable. So we can choose a set of alphas and set of betas at each of these endpoints so that we can make some linear combination of the thing and its derivatives vanish. And we can't have two zeros, basically. So it turns out that you can show this, and this is important, and I'll explain why in a second. So let's say that we have a differential operator with yada yada boundary conditions. If you can write it in this form, so these are second order differential equations. We're going to have one derivative there, one derivative there. So think about like second order differential equations. F equals ma, second order differential equation. So obviously this is important for us. If you can write your differential equation in this form, then the solutions you get out, so lambda might be chosen by you. There might be different lambdas. The set of y sub lambdas, y's for different lambdas, form an orthonormal basis on that interval. Why is that important? It's important because what's happening in general in physics is that nature is doing stuff and we're just trying to describe it mathematically. So the idea that our mathematical representation, we have this guarantee that our mathematical formula and set of functions we get out is an orthonormal basis means that the math can actually represent reality. So reality picks some function y of x. Like this is really what's going on your spinning rope or something like that, which is a Bessel equation, or your quantum harmonic oscillator, which is a little bit more mysterious and invisible. If you can put your math that you derive to describe this in this form, it's guaranteed that your math will actually be able to describe the real answer. So that's what a basis means. Anything you can write down can be represented like this. So I'm going to introduce some terminology. If you've been through quantum or modern, some of this will sound a little bit familiar. And then we'll just do 3 examples, and then I'll give you a hint about the one that you're supposed to do, which is Bessel's function. So I'm going to rewrite this in a little bit different way, since we're now cool with writing differential operators. So this is a differential operator, L, acting on y. And then we're going to rewrite this as plus, just pull the other term onto this side, wxy equals 0. Okay. And this is a type of differential operator that's known as self-adjoint. And these two things will also have more important terminology, the weight and the eigenvalue and the eigenfunction. So L is a differential operator. We can put our equation into this form using L. Y are called the eigenfunctions. Of L. And if you're thinking quantum mechanics, you're right. So think about that as like Schrodinger's equation, and that is the energy, and you're on the right track. Lambda are called the eigenvalues of L. A particular lambda would be the eigenvalue associated with a particular solution y. So that's why we have y sub lambda. And we have w of x is called the weight. And the reason we're doing this now in the quarter is we finally have an example of something that has a weight when we solve the quantum harmonic oscillator. So, and again, what orthonormal basis means is that if you have 2 different solutions, so we have y, I'll write this in the most awkward way possible, lambda 1 of x is a solution, and y lambda 2 of x is a solution. So heard you like subscripts. We have subscripts on your subscripts. And what I should do, since I have this terminology, I should use it. So these are eigenfunctions of L with potentially different eigenvalues. So then, and this is the role of the weight, this is what Sturm-Liouville tells us, is that the integral over our interval, so the interval is from a to b, of weight of x, y lambda 1 of x, y lambda 2 of x, dx is equal to delta lambda 1 minus lambda 2, or if these are not continuous, they're discrete, Kronecker delta. So that's what a basis means, right? In the same way that the dot product of two different basis vectors should be 1 if they're the same and 0 if they're not. Now we're just doing that with functions. And the full Sturm-Liouville theory involves a weight. So now we have, again, one example of that, and we can go through it. So sit here, pause the video, just drink all of this in. So again, this is really important, even though it seems kind of geeky and obscure. What this is really telling us is that the math works and describes nature. Okay, provided your physics can put the equation in this form with those boundary conditions. Easy, less easy. So our first example, we'll do Legendre's equation, because it's got a few moving parts. And this came out of the spherical polar coordinate Laplace equation, right? So we separated out the radial part and we were left with the axial part, and we got Legendre functions out of that. So just as a reminder, when we did that, we set x equal to cosine of theta, and x, therefore, because cosine of theta for azimuthal, or the axial part goes in between 0 and 1. This goes from 0 to 1. Okay, I'm just not going to write all the cosines, because that would be really clumsy. So the other way of saying it is A is 0 and B is 1 in the original description. Okay, so we'll write down what that was. So we beat things into this form. And the reason to do this first is we actually really can read off the Sturm-Liouville correspondence directly from this. It was pretty easy. Right? So that was Legendre's equation after we made this really nice change of variables. Well, I can just do one thing. So I have a first and a second derivative. But I also see that I have x squared there and 2x there. So it turns out this is a total derivative, which gets me exactly what I want. I can just rewrite the above like this, and you can verify this is true. And I'll put a big space there, because it turns out we don't have a q. And we did nothing to that, so that kind of came for free. Okay, so reaching back into my memory, I know what the Sturm-Liouville form is. And I have the d by dx, I have the y prime. This is p of x, right there. And then this is my eigenvalue. And I have no q of x. So I would say that, yeah, I have p of x equals 1 minus x squared. I have q of x equals 0. I have lambda equals L times L plus 1, and I have no weight function. Well, I don't have no weight function. I have a weight function of 1. So this is eigenvalue times no function of x times y. So that's just mapping that onto the expression of Sturm-Liouville operator in theory. So what this means is I just look at it and I examine it and I see that I can pick out a p and a q and a lambda and a w. They don't have to be interesting. I just have to be able to do it. They can be 1s and 0s. And now I just know that the solutions, so my conclusion is that the things that we got that solve this, so the Legendre polynomials, and the first ones were 1, x, 3 halves x squared minus 1 half, da 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 da. These form an orthonormal basis on the interval from 0 to 1, which means if you pick 2 of these and you integrate from 0 to 1, what you're going to get is they will be 1 if they're equal, and they will vanish if they don't. Okay. So, a second to drink that in. Next one we'll do is easier. In fact, this one's like almost so easy it's confusing because it doesn't really have much of anything going on in it. So let's look at the classical harmonic oscillator. And there are 2 ways of phrasing it. You could talk about this as standing waves on a fixed string. That makes the boundary conditions easier to think about, fixed to some value at both ends of the string. Or you could think about this, it's easier to conceptualize, and just letting you guys know you can use different variables, doesn't have to be x. We could think about this also as the mass in a spring. So as an example, and this would be something that maybe goes over the entire interval of negative infinity to infinity if I think about time. Let's talk about the classical harmonic oscillator, which is a block on a spring moving on a frictionless surface. And the spring has a spring constant k, and the mass has a mass of m. And this is F equals ma. It's just F equals ma. So ma, 2 time derivatives. And then the force is negative spring constant times y. So y would be how far this thing moves. So I probably should have called it x. But that's a little bit confusing. So y is just the position coordinate, in this case back and forth. Okay, so this is F equals ma. And I see a second order differential equation. And I know that at least the time derivative doesn't vanish at negative infinity, infinity. So I can use those boundary conditions that I erased. And let's see if we get a set of orthonormal functions out of this. So first I'm going to clean this up. I'm going to call this y double prime. Prime means derivative with respect to time. And I'll call this minus omega naught squared y equals 0. So I want to put it into the equals 0 form with omega naught equals root k over m. So the usual treatment of the classical oscillator. Right? So second order differential equation, we got a constant times the thingy. This is going to be the eigenvalue and the eigenfunction. I can just kind of guess that already. But let's do the work to map it onto the Sturm-Liouville form. So I can turn this into d by dt of 1 times dy dt plus 0 times y of t minus omega naught squared, or if I really wanted to be silly about it, plus negative, oops, sorry, that is a plus, plus omega naught squared y, put that over, plus, equals 0. Okay, so stop for a second, see if you can read off p, q, w, and lambda. Hopefully you can. So this is p of t in this case. This is q. Weight is 1, and omega naught is lambda. So we would say for this, p of t is 1, q of t is 0, omega of t is 1, and lambda equals omega naught squared. And this is in Sturm-Liouville format, and this means that the solutions that we get out of this, you get sines and cosines out of this, or complex exponentials if you're comfortable with doing that. So weight is 1, so 1 times the appropriately weighted sine, and we'll just say the sine has, there's one omega naught and there's a different omega naught, so we'll call it y1 and we'll call it y. Geez, we're already running out of Greek letters. How about y mu and y nu? Dt equals delta mu nu. So if I have essentially, these are going to be proportional to sine and cosine, so we got to figure out how to normalize them, which is tough because we're going over the entire real line. But y mu, for instance, would be proportional to sine mu of t. And if I multiply one sine by another sine with different scale factors inside of them, I do get a Dirac delta function. So we went through that argument when we introduced the Dirac delta function. So good. And this means that anything that we want to express in terms of the motion of something wobbling back and forth, we can do so with sines and cosines. And so that's kind of Fourier's theory in some sense, is that you can express anything you want in terms of sines and cosines. OK. Let's do a harder example that has a weight. And that's the quantum harmonic oscillator. And only the quantum harmonic oscillator after we had this brilliant idea of separating out the asymptotic behavior to get Hermite's differential equation. And remember, we got that talking about the quantum simple harmonic oscillator with the asymptotic behavior pulled out. So the part where it dies exponentially in the classically forbidden region. And what that looked like, so let me just remind you of what that looked like. So we wanted the wave function. And the first thing we did was we turned it into these nice unit-free scaled out coordinates. So I'll keep using psi, squiggly. And we got these polynomials times what we kind of knew from an argument beforehand was the part where it dies in the classically forbidden region. So this will generate a differential equation on H itself. So we solved that. We solved it with recursion. But I'm going to use Sturm-Liouville theory to guarantee that the solutions we got actually made a set of an orthonormal basis. So this is kind of after the fact, just making sure that our solution would actually represent everything we needed it to. OK. So I can rewrite that in the following way. We'll do this. Clearly, H only depends on psi. So I'll just write dH d psi. Right? Is that right? That's right. OK. So same thing. Stare at this. See what P is. See what Q is. Aha, we finally have a weight. See what lambda is. So looking at this term, we have P of psi is this. No Q, so plus 0. So Q of psi is nothing. This unknown but fixed value is the eigenvalue. We could just call it n. The 2 is, whatever, kind of inconsequential. But now we have this, the part that we separated out from the asymptotic behavior still hanging around, and that's going to turn into the weight. So we can put it in this form. We've got P of psi is e to the minus psi over 2. Q of psi is 0. Weight of psi is also e to the minus psi over 2. And lambda is equal to n, or 2n. Ta-da. Again, what this guarantees us is that our h's will form an orthonormal basis. And these were the Hermite polynomials. So having seen all that, it's really just kind of understanding and mapping problem. I will not do this again, because this is for you guys. I will give you 2 hints about how to do this for Bessel's equation. So this is the form of Bessel's equation that we generated in class. So it looks like y double prime, there was a row here. I'm going to call it x. So we did this by separating variables for the cylindrical version of the Laplace equation, plus k squared minus m squared over x squared, y equals 0. Hint 1 is to multiply everything by x. And you can see how that's probably going to work to your advantage, because then this becomes a total differential term much more easily. We have x times y double prime and then just y prime by itself. So that's hint number 2, or hint number 1. Hint number 2 is that q of x is not 0 in this case. Okay. So the other point of doing that is you realize, so we got these two constants when we separated variables. We got a k and an m when we separated the z, and then when we separated the radial part. So we have two constants. You're going to be able to rewrite them in such a way that there's really just one kind of uber constant associated with the eigenvalue. Okay? So good luck with that. Ask questions if you run into them.